Parameshwaran Sankaran. I just have a couple of things to say about this enriching mathematics education program. So this is part of IMSC outreach program. We would like to engage with the mathematical community in Chennai at all levels. So we have a program for school teachers, that is this one, and we also have a program, outreach program for school students, that will be sometime in November, and we have program for college teachers. The program for school teachers, we cannot teach you to teach because you all have several years of teaching experience. You do much more teaching than we do. Our idea is to share our insights about mathematical topics which you would be teaching, you have been teaching, and that's the main aim. And we like to make it informal, so there is no formal inauguration. We value your time, and so we don't believe in elaborate inauguration and so on. You feel free to interact with faculty members here, and also you can talk to each other, and if you have any questions or something, you can ask us. There is also a discussion hour tomorrow in the evening, as was mentioned in the timetable. About our outreach program, there is some write-up in the notebook given to you at the last page, I was told. So I now request our director, Professor Balasubramanian, to say a few words about activities of IMSC. Balu.
Yeah, about this program, of course, Parameshwaran has already talked enough, and this institute has taken as a responsibility of having good outreach programs and to be able to interact with the mathematics students, mathematics teachers in the high school, college level, within the city to a large extent, and as well as in the national level to a certain extent. And this national level, which we do by having some visitors programs, adjunct professors, associates, and so on and so forth. And the students also, we have some visiting students who are doing PhD. And first of all, I should thank the Department of Atomic Energy, which gives us the funding as well as encourages to do all this. And in fact, of the DAE Institute, this particular institute seems to be more well known for its outreach program, mainly due to people like Parameshwaran and Raghavan as individuals, and probably the theoretical computer science as a group, which they are doing a lot of outreach programs. And Parameshwaran, Shankaran and Vishwanath have been instrumental in running such programs every year. Last year also they did it, and I should really thank and express my appreciation for them. And also I should appreciate those who have offered to give lectures here, including Meena and Vishwanath and Srinivas and Anirban, who will be giving lectures on this. And exactly as Parameshwaran said, that we are all open. Anytime you want, you can sort of discuss any of your problems with any of the faculty members here, and we have a library, and I do not really know how useful this library would be for you. It may be of a slightly highly advanced level. But however, let me say one more thing which is very important, that for mathematically inclined students, this is true only for mathematics, but even for physics, chemistry, etc., there are something called Olympiad programs. Okay. These Olympiad programs, first of all, takes place in the regional level, and then all those 30 people are selected in the regional level, I assume, and then all those compete in the national level, and out of which 30 are selected, and then out of this 30, then again another training is given, and 6 are selected, and 6 goes to the so-called the International Mathematical Olympiad. And the same thing is true, of course, of physics, chemistry, and so on and so forth. But the fact is that those things are done by different group of people whom I really have no idea about. But on the other hand, the mathematics is being done by something called the National Board for Higher Mathematics, with which I am associated. And therefore, I would probably encourage all of you to know a little more than your syllabus, okay? Particularly things which are what one may call as the discrete mathematics and number theory and a certain geometry, because that is the only subjects in which a person in the plus 2 level can be actually tested. And therefore, the Olympiad program would be essentially in those areas only, the discrete mathematics, number theory, and some geometry, Euclidean geometry. And if you can train your students, then you see, if you do in initial training and if they qualify, then the later, for the later purposes, of course, we have enough resource people to train them. First of all, when they cross the first stage, then we have a big group of people to train them in the second stage to third stage. We have a big group of people from third stage to fourth stage, and so on and so forth. The only question is from the first stage to second stage. And if some of you can take some time off from your teaching and identify good students and teach them, so that they would be able to do the Olympiad program at least in the first level and come up to the second level, that would actually give you a certain visibility to your department in your school. And you can also write on your CV of your school, etc., that the Olympiad level they have gone, and so on and so forth. And in that particular condition, we are actually trying to get some books on the Olympiad, and I think there is a small section of the Olympiad problems that at least would be useful for you. And therefore, I will definitely request you to spend some time there in the Olympiad things, and the discrete maths and the number theory, etc., which you are learning here would definitely be of useful to you to be able to train those students. Okay? With that request, let me welcome you once again. Thank you.
Before I hand it over to the next speaker, who will introduce himself, I'll have two announcements. One is that lunch is on the other side of the road. So follow, there is, I'm sure some people who know where it is, so follow them across the road. Okay, and then if you want, the photographs will be put up on the net. If that is good enough, that's fine. You can always access it. It will be available from the web page permanently. But if you want a hard copy, you may sign up for it with somebody outside. Okay, there will be people this afternoon or also tomorrow morning with at the registration desk. If you want a hard copy, you can give them your name. With this, I hand over the. Yeah.
Announcement I forgot, particularly since the majority of the teachers whom I see are women. Let me just point out that so far for this Olympiad program, we have been choosing 6 people and sending to Olympiad. And from this year onwards, we have decided also to send women students for the Women's Olympiad program. And therefore, particularly those who are in women's schools, etc., should take some special effort, because this is something which is starting this year, and it will be very nice if. And I should also say that in the last 4-5 years, the last 6, out of the last 6, 90% of the students do come either from Bengal or from Pune, and from no other part of the country. Okay? And that, for people who are coming from this Ramanujan's land, should be somewhat a shame. And it is now in your hands to correct it. Okay? And at least the Girls Olympiad program is also starting this year, and please take some efforts to train some of your good students to attend the Olympiad program. Preliminaries, I have no idea at all. There is a person by name Ranganathan who retired from Vivekananda College. Do you know him? Otherwise, I will try to get you the information. That should not be a problem. AMTI. Yeah, the AMTI is the one which does the first original.
But in this institution are we conducting any different exams?
No. There's no different exam. There's only one exam, and the National Board for Higher Mathematics conducts the exam from the second stage onwards. The first stage are given to the local authorities, and as far as Tamil Nadu is concerned, it is done by IMTA. And once they pass this IMTA, I think from the second stage onwards, the National Board will take over.
Hello, good morning everyone. I am K. Srinivas. I work in number theory in this institute. So I will be delivering 2 talks. Okay, so many of you have come previous time also. And see, as has been told here in the morning, that one of the aims that we look forward is, the students have many queries like, what do mathematicians do? What is done in research? Because it's very difficult to say to students, physicists' work one can find out, biologists one knows what they do. It's because it's very visible, geologist, but what does a mathematician do? What is the research that is done in mathematics? That is one of the problems. And the second problem, which is more often asked, is where is it applied? Okay? Chemists can easily say that, we make medicines or something like that. But mathematicians, where is the mathematics applied? So I think we will address some of the questions as we go along. But most important thing is the beauty of mathematics. Okay? The student should be told that mathematics is indeed beautiful. And for that, all of us should first get convinced that it is indeed beautiful. Okay? So we will see some of the ideas, very basic ideas. Okay? So number theory starts with, okay, in my lecture, all numbers are integers. Okay? When I say n is a number, I mean an integer. Okay? So all numbers are like. Okay? And this we denote it as set Z. Okay? Set of integers in my talk. Okay? And when we say that an integer a divides another integer b, we write it as, so a divides another integer b. What is the meaning of this? B is a integral multiple of a. Okay? That's important. This means b is some a times k for some integer k. Okay. And many properties are very clear from this. For example, a divides b and b divides c. This will imply that a will divide c. Okay? This is very clear. And similarly, suppose a divides b and a divides c, then a will divide b plus c, a will divide b minus c. A will divide an integral multiple of b and a will divide an integral multiple of c. Therefore, we can say that this implies a will divide b times some integer x plus c times some integer y. So these things follow from the definitions. Okay? Many things one can write down, very beautiful things. Having this definition, the first theorem that one encounters is what is called, popularly known as, division algorithm. Okay? What does it say? Given any two numbers, A and B. You divide A by B, you get a quotient and a remainder. But there is nothing great about this statement. What is great about the statement is this Q and R. If you impose some conditions, then they are unique. For example, 17 and 7, suppose we are given, or 5, two integers are given, we divide 17 by 7 is equal to 5 times 3 plus 2 we can write it, or we can also write is 5 times 4, which is 20, minus 3, or we can write 17 as 5 times 5, 25, plus minus 8. There are infinitely many ways of writing. But division algorithm says that if you restrict the remainder less than the divisor, then there is only one way of writing it. So this is the only one way. Therefore, let us state it. Given A and B, let's say B positive, we have A is equal to, that means we can find Q and R integers such that A is equal to B times Q plus R.
Sir? Yes. B is equal to AQ plus R.
See, I mean, it's not necessary that B should be less than. See, because if I have to divide, see, for example, suppose I divide 6 by 7. How will I write? 6 is equal to 0 times 7 plus 6. So 6 is always less than 7. I am dividing it by 7, okay? So we are not bothered right now. For simplicity, we are only taking positive integers, okay? Otherwise we have to put a mod, absolute value. So this R will be less than the divisor B, and R may be, it may be equal to 0 also, okay? What is important is the expression 1 is unique. That means given any A and B, there is precisely one pair of Q and R. Okay? This is the meaning of saying that this is unique. Well, this has lots of applications. We apply many places without perhaps realizing it. Okay? So that has to be told to students that at several instances, how this thing is applied. One of the simple examples, in today's class we will develop some basic notions, and tomorrow we will see some applications. Okay? For example, every integer can be written expanded in the decimal expansion. Every integer has a decimal expansion. For example, n is an integer, then we can write it as A0, its units digit, plus A1, 10, plus A2, 10 square, plus AK, 10 to the power k. This is usually how we write decimal expansion, okay, to the base 10. And what is this A0, A1 all these things, they are the digits of n. This k plus 1 digits are there. Okay? And what is the condition that is imposed on A0, A1, A2, AK? They must be not necessarily greater than 0. Some of them can be 0. Not only non-negative, all these AIs, they are less than or equal to 9, bigger than or equal to 0. Right? For I is equal to 0, 1, up to k. Where did we get this expression? Right? This from here. We are given n. To find its units digit, we first divide it by 10. So we get units digits, A0. Then whatever is there, we divide it by 10 again to get the 100th second digit, 10th digit. Okay? So this has to be, usually what happens, we present them as an individual isolated pieces. We must correlate the things. Okay. Therefore, and it is not necessary that the base should be 10 only. For example, if you are working with computers, computers understand binary digits. So we can take it to be 2, base 2. Then all the numbers are either zeros and ones, a sequence of zeros and ones. Okay? So this is one of the things. Another concept, important thing, is the concept of greatest common divisor. Given two numbers, there is a GCD and which is unique. Okay? A and B. Look at all the common divisors of A and B. Choose the one which is the largest. That is a GCD of A and B. Okay? Positive divisor. And we denote, this is the symbol to denote the GCD. Okay? Suppose we can say that when we say D is the GCD of A and B, we mean that D divides A and D divides B because D is a common divisor. And D is largest such. That means if you take any other divisor of A and B, okay, divides that one. So D divides A, D divides B. So D is first a common divisor. Okay? And if K is any other divisor of A and B, then K will divide D. Okay. How to find? For small numbers, we can factorize the number A and look at the factors of B, look at what are the common factors of A and B, and choose the one which is the largest. But if the numbers are very large, factoring takes time. Factoring is not so easy. Okay? Therefore, what to do at that time? And here, again, the Greeks have told us how to find the GCD. It's one of the most novel ideas. Euclid, around 300 BC, he gave us a method, algorithm, Euclid's algorithm, how to find the GCD of two numbers, however they are large, in a very easy way. And his method can be written as A and B. The GCD of A and B is same as, suppose A is bigger than B. There are two numbers, different, okay? A is bigger than B, then the GCD of A and B is same as the GCD of A minus B and B. So this is, you can call it as a theorem. Okay? And in mathematics, you know, proofs, unless you prove a statement, it cannot be called as a theorem. Okay? Mere examples do not prove a statement. Okay? They are just illustrations. So sometimes it is nice to show students what a proof means, how to prove such simple statements. Okay? Here is a positive number. Here is a positive number. You have to show that they are equal. Okay? So take this equal to D, and suppose this is equal to D prime. Okay? Since D is the GCD of A and B, D divides A, D divides B by definition. So D divides A, D divides B. Okay? Now, D divides A and D divides B means D divides A minus B. So this implies D divides A minus B, and this statement is D divides B. Now if D divides A minus B and D divides B, D will divide the GCD of A minus B and B, right? So therefore, D divides the GCD of A minus B and B. Because D is a common divisor, it will divide the greatest common divisor. And this is nothing but D prime. So D divides D prime. So this we have got, that is IE, that is D divides D prime. Now flip the argument. D prime divides A minus B, because it's a common divisor. GCD means it's a first of all it's a common divisor. So D prime divides A minus B and D prime divides B. Therefore, D prime will divide the sum of these two numbers, A minus B plus B, which is A. So D prime divides A and D prime divides B. Therefore, D prime is a common divisor of A and B. And since it's a common divisor of A and B, therefore it will divide the greatest common divisor of A and B. Therefore, D prime will divide D. Okay? So D prime divides D. D prime divides D and D divides D prime. That means D is equal to plus minus D prime, right? But since both are positive, they must be equal. Because we are dealing with integers only, one integer divides another, the another one divides this, means they can be plus minus. But since we are dealing with positive integers only, so they must be equal. Therefore, this shows that D is equal to D prime. Okay? So let's take an example. Let's our famous 17 and let's say 7. So what does it say? 17 and 7, GCD of these two numbers is same as 17 minus 7 and 7. So this is 10 and 7. We can still subtract one more time. So this is same as 10 minus 7 and 7, which is 3, 7. But I mean, this is just an example. We can take large numbers. Subtraction is easy. Rather than factorization, so we can subtract two numbers quite efficiently, quite easily. Whereas factoring numbers is very difficult. Okay? So 3 and 7, if you want, you can further do it. 3, 7 minus 3, which is 3 and 4. Further you can do it. 3, 4 minus 3, which is 3 and 1. If you want, you can further do it. Okay? So this is 3 minus 3 times 1 and 1, This is 0 and 1, and therefore this is 1. Okay? Where is division algorithm coming here? Please think about for a minute. Where is division algorithm?
Excuse me. Yes. 3 comma 4, then 3 comma 4 minus 3 is 1, then 3 comma 1 is 1.
Yeah.
And the next one.
3, see this is smaller one, right? So I'm subtracting it 3 times. 3 minus 1 comma 1, again 3, so 2 1 I've got. If you want I can do it like this. 3 comma 1 right here. So 3 minus 1 comma 1, which is 2 1, again 2 minus 1, 2 minus 1 comma 1, which is 1 comma 1. I can subtract one more time 0 1, okay? Or you can say 0 comma 1 1, okay? So you see this division algorithm, what we are doing is division algorithm precisely. Yes. So 17, we are dividing it by 7. Okay? 17 is 7 into 2 plus 3. Okay? And then 7 is equal to 3 times 2 plus 1. 3 is equal to this 1 times 3 plus 0. The moment we get a non-zero reminder, I mean just the reminder before the 0, that is the GCD. So here this is the GCD. Okay? This is what precisely we have done here. Okay? You can write it in symbols A, B. So A is equal to B1Q plus R1 and B divide R1 by R1. Keep doing that. That is what is called Euclid's algorithm to find the GCD of two numbers. As a byproduct, we get something else. For example, here 1, which is the GCD of two numbers. So 1 is nothing but 7 minus 3 times 2. We are working backwards. Okay? Now this 3 is coming from here. Okay? So this is 7 minus 3 is 17 minus 7 times 2. 17 minus 7 times 2 times 2. So this is how much? 1 times 7, 4 times 7. So this is 5 times 7 minus 2 times 17. 2 times 17. This is same as writing minus 2 times 17 plus 5 times 7, which is equal to 1. So what did we get? GCD, given any two numbers, we are able to find out integers x and y such that the GCD is x times a plus y times b. So as a byproduct, we have also solved a linear equation. I mean, in the sense, the GCD we have expressed as a linear combination of the numbers a and b. Okay? It's a very important and very beautiful thing. See how many things the Greeks have left to us. Yes? Yeah, so GCD, what is GCD of, let's say, minus 4 and 12? Okay? Something like this. Okay? So when we say GCD, we always mean the positive divisors. Okay? So minus 4, the factors of divisors of minus 4, you can say that minus 1 is a factor, 1 is a factor, 2 is a factor, 4 is a factor. We will only look at the positive divisors of this number. And for 12, 1, 2, 3, 4. And therefore, since 4 is the greatest, so we will say that this is 4. Okay. So, yeah, therefore, yeah, so we can write it as, so we have a theorem that if D is the GCD of AB, then we can find integers x and y such that D is equal to A times x plus B times y. Okay? So GCD can always be written as a linear combination of A and B. Now let me ask you a question. Suppose I give you an equation 12x plus 21y is equal to 7. Okay? Does it have a solution? Can we find any x and y such that this is satisfied? No, I am talking, all my numbers are integers. 1 by 3 doesn't exist. I don't know what is 1 by 3. I started with that stuff. All the numbers that I know are integers. What is your guess? Infinitely many. Anyone else? Multiples of? No, I just want, since you said infinitely many, I just want one solution. Not possible? Positive or negative, whatever. Yeah, negative is also allowed. Not possible. The one candidate who says not possible, many are saying infinitely many. Majority should rule. What is, I mean, there is very few answers. Please, even if it is wrong, doesn't matter. Please tell us, tell me. So how to argue this kind of thing? Suppose there is a solution, okay? Suppose there is an x and y. You look at left hand side, okay? Here is 12, here is 21. There is a number 3 which divides 12 and 21. So whatever the x and y, the left hand side is a multiple of 3, whereas the right hand side is not a multiple of 3. So that's all. Okay? So LHS is a multiple of 3, whereas RHS is not. Therefore, no solutions. Okay, it's very easy to guess. Okay? On the other hand, If I give you, let us say 3x plus 14y is equal to, let us say 7 again, you can find solutions. Okay? Why? Because 3 and 14 are co-prime. Therefore, their GCD is 1. And GCD can always be written as a linear combination of x and y. So you can find some y, okay, so that this is soluble. So you see how all these things are very elementary and they are related. Okay? So question? Yes? Okay. So what I am saying, 3 and 14 are co-prime. Co-prime means they have no common factors. Their great GCD is 1. Okay? And we have seen that the GCD can always be written as an integral multiple of A and B. Therefore, this 1 we can write it as 3 times sum A plus 14 times sum B. For sum, we can find out A and B. Okay? But that is what we wanted. Okay, so you multiply it by 7 there. So 1 is equal to 3a plus 14b. Then 7 is equal to 3 into 7 times a plus 14 into 7 times b. So x and y are found. Once you find this a and b, for example, what is a and b here? In this equation, can you guess, just say what can you say about a and b? See, for example, a is 5 and b is minus 1 is a solution. So a is equal to 5 minus 1, and therefore you put 7 times this thing. So x for this equation, x is equal to 5 into 7, 35, and y is equal to minus 7. Okay? You can see that if you multiply and see that, that's a solution for that. Okay? Okay. Question that I wanted to give you is, write down conditions so that ax plus by is equal to c will have solutions. Okay, you are given an equation ax plus by is equal to c, a, b, c are integers, not 0, and we have to find out under what conditions we have solutions for this, under what conditions it will not have solutions. So discuss the solution of these things. So we will discuss it later. Okay, you can discuss among yourselves, and we can discuss it later also. Okay, in the leisure time and tomorrow also. Okay, so this is about these things, GCD. Okay. Now, as you know, composite numbers, for example, numbers are categorized into two things. One is prime numbers, another is composite numbers. How do we define a composite number? More than 2 factors. Okay. But we can, in a compact way, we can say that n, let's say n is a number. We say that it is composite if n can be written as product of 2 numbers a and b with some conditions. A is not equal to 1 and b is not equal to 1. That much will suffice. So n is composite provided we can write n as a times b with strict inequality. A and b strictly should lie between 1 and n. Right? So this is the way of what you have said, more than 2 factors. It means the same. Okay? Because only 2 factors means 1 and itself. But here are more than 1 and itself. 1 and itself is of course a factor of this, but there are other factors a and b, so which is lying between 1 and n. Okay? Okay. This is number 2. From here, what can you say about the size of a and b in terms of n? Okay? I mean, how large can be or how small can be a and b? For example, can a and b, can they be both bigger than square root of n? Okay? Question. Can a, b both it is not possible. Okay? Because if it is true, then a is bigger than square root of n, b is bigger than square root of n, their product will be bigger than n. Therefore, it is not possible. Therefore, what is possible? One of them must be less than square root of n. Okay? That is a conclusion. So, it is not possible. And not possible implies the negative is true. Okay? That is not possible means its contrapositive is true. So, this implies one of a or b must be less than or equal to square root of n. Okay, that is the conclusion. And such a simple statement has again lot of applications. Okay? Yes, any question? Suppose I give you a number 93. Is it prime or not? How do we know? Because we divide it. 31 divides it. Suppose I give you 91. Okay? Yeah. But the thing is, here to save time we are taking small numbers. But supposing we write large numbers and ask the question. Okay? Now, when we say that it is prime or not prime, if it is composite, it will have a prime number, prime divisor. It will have a divisor which is less than square root of this number. Okay? Now, one thing is every number, a composite number has lot of factors. You keep dividing, ultimately you can write it as a product of primes. Right? N is a and b, If A and B are both composite, you can further write it as A1, B1, A1, A2, B1, B2. So ultimately, you can arrive at a product of primes. So every number has a prime divisor. Therefore, this number will have, if it is composite, it will have a prime divisor P, which will be less than or equal to square root of 91. What are all the primes which are less than square root of 91? What are all the primes which is less than square root of 91?
2, 3, 5, 7.
Only few primes, 2, 3, 5 and 7. Because the next prime 11 square is 100 more than this one, okay? 121. Therefore, whether this is prime or composite, enough to check with this, only these 4 divisors. So, 2 divides this, it doesn't. 3 doesn't. 5, no. But 7, yes. Therefore, so only 4 steps are enough, rather than thinking and looking and all these things. So, even if you are given a large number, this process is very efficient. Okay? So, this is one of the things. It gives you a primality testing, in the sense whether a number is prime or not. So, what is?
Number finding square root and finding all the rest of divisibility up to 19 or
See, supposing you have a digit which is 400 digits, a number with 400 digits, then this is not efficient. There are other ways. But for small numbers, it is quite efficient. Okay? Now, I mean, even 1009, whether it is prime or not, this method will tell you very efficiently. Okay? Such small numbers we can manipulate, use this method quite easily. Okay. So, this is one thing. A beautiful application of this is, suppose you are given only this many primes, all the primes up to square root of 100. So, 2, 3, 5, 7. Okay? With these primes, we want to generate more primes. We are given only question, find all primes this is a question. So, what we do? We will make a table of numbers 1 to 100. 1, 2, 3, 4, 5, 6. And go on like this. So, here is 100. Okay? And we are given only these primes. Okay? Now, sorry? First, let us compute up to 100 and then we will go up to whatever number you want, we can do. Okay? 2 is prime, that we know because we are given. Now, remove all the multiples of 2 in this list. So, 4 goes away, 6 goes away, 8 goes away, 10 goes away. Okay? Retain this 3, remove all the multiples of 3. So, 6, 9 and so forth goes away. Retain this 5, remove all the multiples of 5. Okay? So, 25 and all this 15, all these numbers goes away. Retain this 7, remove all the multiples of 7. That is all we have to do. So, many numbers have gone away, but still some numbers are remaining here. Okay? And whatever number is remaining, they are all primes. Sorry? 1 is not a prime. Okay? Yeah, this is not a prime number. So whatever numbers are remaining in the table, all of them are primes. Are you convinced with this, all of you? That's precisely because of this statement. If some number, if supposing some number is there, if it is not prime, then it will have a prime divisor less than square root of this. But we have removed all the multiples of those numbers. So no composite number can remain unchecked. Therefore, whatever is remaining, so we have got all the primes up to 100. Now, if you want 1000 or 10,000, you have primes up to 100, make a table up to 10,000 and keep doing that. Okay? So this was given to us by sieve of Eratosthenes. Okay? Okay, these are some of the important things. Okay. Now the next concept is, another thing, since I am talking about primes, how many primes are there? Total number of primes. Total number of primes. Infinite. And how do we know that? Huh?
The numbers are in prime, that's why you have to infinite only.
Numbers?
Numbers are in prime. So prime should be also, numbers should be also infinite.
No, numbers are more than primes, no?
Yes. But still, sir, numbers are unending. Primes can also not end.
No. That's, see, the set of numbers is much larger set than the set of primes. But if larger set is infinite, doesn't mean that the smaller set is infinite.
But here we apply it.
Huh?
But here we apply it.
No. So how do we, how do we know? I mean, can we simply prove?
Sir, if I'm taking the set of all numbers, I'm taking a multiple of 2.
Taking?
Multiple of 2. I have a one-to-one correspondence.
One-to-one correspondence between?
Between the multiples of 2 and all the numbers set, which I have taken a subset.
So f of n is 2n. Yeah, but you have shown the one-to-one correspondence with an infinite set. Therefore, it is infinite. But can you show an one-to-one correspondence between primes and integers? We cannot, because we do not know where is the next prime lies. Primes do not follow any regular pattern.
Yes? K is the biggest prime. K factorial plus 1. It's a prime. It's not itself.
K factorial plus 1 need not be a prime number. It may be a composite number. It may be a composite number. Yeah, it is not divisible by all primes up to k.
No, if you are writing one number n as the prime product of all prime numbers up to the biggest prime number.
So there is some assumption here. Suppose, okay. So right. So again this goes to Greeks. Okay. So what is the argument? Yeah, I'm explaining your argument. What Euclid again he did was, you look at the number 2 into 3 plus 1. Okay? This is 7. Now 2, 3, 5 plus 1. So let me write it down to save time. This is 31, and then 2 into 3 plus into 5 into 7 plus 1. This is 211. 2 into 3, 5, 7. Next prime is 11 plus 1, 2, 3, 1, 1. Take one more prime, 2, 3, 5, 7, 11, 13 plus 1. This is 30,000, 031. Okay? You can see that this is a prime, this is a prime, this is a prime, and this is a prime. Okay? But this is not a prime number. Okay? You can show that this is a multiple of 59 times 509, I suppose. 509. Okay? So what was the argument of Euclid? You look at all the primes. Okay? Add 1 to it. In all these cases, you got a new prime. Okay? In this case, you got a number which is composite, but it is a product of two numbers. This is a prime, this is a prime. And these primes are bigger than 30. Okay? So, the Euclid's argument is, given a set of primes, let's say 2, 3, up to p, you are given a set of primes, p prime. P is the, up to p primes you are given. You form the number 2, 3, 5, up to p plus 1. Call this as n. Okay? Two possibilities for n. Either it is prime or composite. Okay? If it is prime, certainly it is larger than p, much larger than p, because it's a product of all this plus 1. But supposing it is composite, then it is not divisible by 2. It is not divisible by 3, because n cannot be divisible by 2, because this number is divisible by 2. If n were divisible by 2, then this number minus n will be divisible by 2, but this number minus n is 1. Okay? Therefore, n is 2 does not divide n, 3 does not divide n. By the same reasoning, p also does not divide n. If p divides this, p divides n and p divides this, then p will divide the difference, and the difference is 1. Therefore, p will divide 1, which is not possible. Therefore, n has a prime factor which is bigger than p. In either case, we have exhibited a prime which is bigger than these primes. So, one more prime. So, therefore, it shows that there are infinitely many primes. Okay? So, this is the brilliant idea of Euclid. Okay? And you know, this is so simple and elegant that it has percolated to us, you know, from civilizations to civilization, the novelty of this idea. Okay? They were not what is the most natural way of showing that something is infinite? You look at the next element. Okay? Number of natural numbers is infinite. So, you take n be the largest, add 1 to it. That's again a natural number which is bigger than n. Therefore, there is a contradiction that n is the largest natural number. So, you look for the next one. But Euclid did not look for the next prime. That is the brilliancy. He said, let me not look for the next prime, because I don't know where is the next prime. I look for a prime which is bigger than the given prime. And he was successful. Here, the next prime after 13 would be 17. He didn't bother about that. I want a prime which is bigger than 13, which is 59. That's it. And that, that's the brilliancy. Okay? So such ideas can come only if you have some feeling for the subject. Okay? Fine. There is a beautiful function. So therefore there are infinitely many primes. I will not go into details of that. This is a very nice function. This is called Euler's tangent. Euler's tangent function. It counts the number of integers from 1 to n which are relatively prime to n. Okay? So this is number of integers less than n and relatively prime to n. For example, what is phi of 7? What is phi of 7? All the numbers less than 7 which are relatively prime to 7, not 3. Answer is what? See, I have to look at 1, 2, 3, 4, 5, 6. And let me write 7 also. Let me write it less than or equal to. Doesn't matter. Okay? Of these numbers, I want to look at all those numbers which do not have any common factor with 7. That means the only common factor should be 1. So 1 is a number, 2 doesn't have any common factor, 3 doesn't have, 4 doesn't have, 5 doesn't have, 6 doesn't have. Therefore, the total number is 6. Okay? Given any prime, phi of p is p minus 1. Because 1, 2, 3 up to p minus 1, all the numbers, because p is a prime, they will not have any common factor. So it is p minus 1. What can you say about phi of p square? Yes. It doesn't make difference. Yeah. So even if you take less than or equal to, it doesn't make any difference. That's all. Okay. So phi of p square, for example. So 1, 2, 3 up to p square, how many numbers are there which are relatively prime to p square? Okay. For example, phi of 7 square. There are 49 numbers, 1, 2, 3, there is 7, up to 49. Of this, how many are there which do not have any common factor with 49? So easiest thing will be first find out how many are there which have something common with 49. Okay? And then remove those numbers. 7 has, and then 14 has. So 7, 2 times 7, 3 times 7, and this is 7 times 7. So there are 7 numbers which are not co-prime to 49. Therefore, total number of numbers minus the numbers which are not co-prime will give you the total number of co-prime numbers. So this is 7 square minus 7. Okay? Therefore, in general, you can show that this is p square minus p. If sometimes you can write it as p square 1 minus 1 by p. Okay? I will just take few more minutes because I've started late also. Okay. Now another thing, phi of PQ. Let's have suppose phi of PQ. Two primes, P and Q are primes. Okay? For example, phi of, let's say, 3 into 7. This is into, not point. 3 into 7. So 1, 2, 3, up to 3 into 7. From here, first remove all the numbers which are not coprime. Okay? The numbers which are not coprime should have a common factor 3 or 7. Okay? Those are the only numbers which are not coprime. So how many numbers are there which have multiples 3? 3 is there, 2 times 3 is there, 3 times 3 is there, 7 times 3 is there. So you remove all of them, not 11 of them, 7 of them are. So 3, 2 times 3, 3 times 3, 3 times 7. And then you remove those which are multiples of 7. Okay? So 7 is there, 1 times 7, 2 times 7, 3 times 7. But you see, we have removed 3 times 7 in the first go. We cannot remove it again, so we have to add this one. Because while removing this, we are removing twice. So add this. So therefore, what we are doing, total number is 3 into 7. These many numbers are there, minus the multiples of 3 are 7. The multiples of 7 are 3. And since we have removed this number twice, we have added once. Okay? In general, phi of PQ, there are total PQ numbers minus P minus Q plus 1. You can see that this is P minus 1 times Q minus 1. And P minus 1 is phi of P and Q minus 1 is phi of Q. So this is phi of P, phi of Q. Okay? In general, so phi of AB, suppose A and B are coprime. A and B do not have any common divisors. Then phi of AB is same as phi of A times phi of B. Okay? By the same argument. And for any integer n, phi of n, suppose n is P1, PQR, something like that. P square, Q to the power 10, and R to the power 15, something like this. N is a number having this kind of thing. Then phi of n is same as phi of P square, phi of Q to the power 10, and phi of R to the power 15, where PQR are primes. Okay? So finding how many numbers which are less than n coprime to n reduces the problem of finding how many numbers are there which are less than P square and coprime to P square times how many are there less than Q to the power 10 relatively prime to 10, q to the power 10, and how many are there which is less than r to the power 15 and relatively prime to 15. And for this we know that this is p square minus p. For this we know that is q to the power 10 minus q to the power how much? 9. For this r to the power 15 minus. If you take p square common here, it is 1 minus 1 by p. If you take q to the power 10 common here, this is 1 minus 1 by q. R to the power 15. So this is 1 minus 1 by r, where p, q, r are the prime divisors of n. Therefore, this is p square q to the power 10 and r to the power 15 times 1 minus 1 by p, 1 minus 1 by q, 1 minus 1 by r. P square q to the power 10 r to the power 15 is nothing but our n. So this is n into what are these numbers? These are the prime divisors of n, p, q, r. So we can write it as, this is the notation for product. Okay? Yeah, and let's not complicate the matters. 1 minus 1 by p, 1 minus 1 by q, 1 minus 1 by r. Okay? Therefore, if I want to know how many numbers are there which are co-prime to, let's say, yeah, 2 to the power 10 and then 5 to the power, or if I say 10 to the power 25, something like this, how many numbers? This is a large number. How many numbers are there which are less than 10 to the power 25 and relatively prime to 25? Counting by hand is difficult. So this is what happens is 2 into 5. So 2 to the power 25 into 5 to the power 25. So now phi of this number is same as phi of this number. And we know phi of 2 into 5, 2 and 5 are relatively prime. So phi of this into this will be phi of this and phi of this. Therefore, this is phi of 2 to the power 25 into phi of 5 to the power 25. But we know what is this much and what is this one. So this is 2 to the power 25. So you can write it as, by using that, 10 to the power 25, 1 minus 1 by 2, 1 minus 1 by 5. This much you can do. Okay? Or you can say that 2 to the power 25 minus 2 to the power 24 into 5 to the power 25 minus 5 to the power 24. Okay? So these are the things. Another thing I wanted to introduce was notation of congruences. Okay? Just let me define that one and then we will pursue it tomorrow. We say that two numbers are congruent, 17 and 7 are congruent modulo 5. Means what?
You say remainder up to
Modulo 5.
That means 17 minus 7 is a multiple of 5. This means 5 divides 17 minus 7.
okay. So actually we need to write a 7 is less than 5.
7 is
17 congruent modulo, that number 7 mod 5, instead of that we need to write that 7 as a less than 5.
doesn't matter, 7 and 2 are same modulo 5. Okay, when we say modulo,
We call that as a residue. Residue is always less than the divisor.
I have not called residue so far. I have not used the term residue. Okay, I am only introducing two numbers, A and B. By definition, A is congruent to B modulo M. What is the meaning of that? It means that A minus B is a multiple of M. That's all. Residues will come later. Okay? So in general, we write as A is congruent to B modulo M. So we take M to be positive. Okay? This means M divides A minus B. Okay? Please pay attention. This also means that suppose you divide A by M, you will have a remainder R by division algorithm. You divide B by M, you will have a remainder R. When A minus B is a multiple of M, that means both A and B will have the same remainder. So that reminders will get cancelled. So A is equal to M times Q1 plus R1, right? By division algorithm. And B is also, when you divide it by M, Q2 plus R2, where R1 and R2 are less than M. Okay? Now, this statement, M divides A minus B. When is it possible? A minus B is M times Q1 minus Q2 plus R1 minus R2. This is M times Q1 minus Q2 plus R1 minus R2. So M divides, so this is already a multiple of M. Therefore, this must be a multiple of M. That means there is 0. Okay? R1 minus R2 must be 0. Okay. So A is congruent to 0 modulo M means what? That means M divides A. Okay? This. So two numbers are congruent means they have the same reminders. And yeah, what you were saying residues is when you look at these numbers, modulo 5. 5 is the modulus. Okay? Take any integer n. When you divide it by 5, the possible reminders are 0, 1, 2, 3, 4. Because remainder is 5 means again it is 0. So all the reminders belong to this set. So modulo M, every integer is associated congruent to one of these elements. These are called the residues modulo M, modulo 5. So these are the residues modulo 5. Okay? And out of this, those residues which are co-prime to 5 have a special name. They are called reduced residues. Okay? So these are the residues. And the another one is reduced residues. Means these are 1, 2, 3, 4. One more example and then we will stop. M is equal to 8, let's say. Modulus is 8. What are all the residues? 0, 1, 2, 3, 4, 5, 6, 7. What are the reduced residues? So reduced residues modulo 8. All the numbers which are co-prime to 8. 1, 3, 5. then 7. There are 4 numbers. These are precisely those numbers which are co-prime to 8. So the cardinality of this set is phi of 8. Okay, phi, the Euler function. Phi of 8 counts the number of integers less than 8 and relatively prime to 8. These are precisely these things. So the phi function is nothing but the cardinality of this reduced residues. And we will see the application of this tomorrow. Okay. So any questions you have, you can ask any time. Okay. So I think we will go for lunch now. Thank you very much.